Greetings and salutations, magical chemists. Today we're going to learn about how to apply Le Chatelier's principle to answering free response questions. Luckily, there is a very straightforward framework that you can use for any Le Chatelier free response. When you are trying to answer a free response question, it is essential that you identify what stress has been applied to your equilibrium system. Basically, what did you change? And then, of course, you want to identify the effect of the stress. Did it make the system shift right, shift left, or no shift? But the problem is a lot of people stop there. You have to go a little bit further when you're doing free response. So it is essential to make sure you connect that the effect of the stress is happening because it's going to counteract the original stress. Basically, you're trying to undo the change to reestablish equilibrium. Of course, you will never actually completely undo the change, but you're trying to undo as much of it as possible. And, with free response, it is always essential to double check that your explanation is actually answering the question. All right, let's take a look at a practice problem. In example number 1, the temperature of an exothermic reaction changes from 25 degrees Celsius to 50 degrees Celsius. Well, what's the effect on the equilibrium constant K? Well, hopefully you can tell, right? Our stress, the change, is that we are increasing the temperature. Notice that they specified we are looking at an exothermic reaction because this answer would be different if it was an endothermic reaction. Exothermic, exiting, heat is being produced, and so increasing the temperature is basically like increasing a product of the reaction. Le Chatelier says to undo that, we've got to shift away from the products towards reactants. Why will that help us reestablish equilibrium? Well, it's using up some of that additional heat. Now, of course, you still have to answer the question. They asked for the effect on K. Changing the temperature does, in fact, change the numerical value of K. But if you increase reactants and decrease products, and you're looking at a product-to-reactant ratio, this is going to decrease the value of K. And now you just put it all together. Increasing the temperature of an exothermic reaction will cause the system to shift left, to use up the added heat, and re-establish equilibrium. That phrase is key. And this shift increases the concentration of reactants, decreases the concentration of products, therefore the value of K decreases, and done. Let's check out another example. In example number 2, we're given a chemical reaction, and we're saying, well, if you add some more of your gaseous A, whatever that is, to the reaction vessel, what effect will that have on the concentration of B? Now, one thing to realize, that if you're adding more gaseous of particle A, that is increasing the concentration of A. And A is a reactant. So if we are increasing the concentration of a reactant, Le Chatelier says we should try to counteract that by shifting away from the thing we added, which means we're going to shift right or shift towards products to use up some of that added chemical. Now, of course, the question specifically talks about B, and B is another reactant. Well, as the reaction shifts right to use up some of the extra A, it has to react with B. So the amount of B overall is actually going to decrease. And then you just squish that together into complete sentences and, yay chemistry. So my version was, adding more gaseous A will increase the concentration of A, a reactant, and so the system will shift right to use up some of this extra A by making more product. Using up some A to make products will also use up some B, and so the concentration of B will decrease as the system shifts to reestablish equilibrium. Now, I was typing that. If I was handwriting this on an actual free response, I totally would have just put square brackets around B instead of writing out concentration of B. And those abbreviations are still totally okay. All right, third example. Same reaction-ish, but notice states of matter. This time, B is a solid, and we want to take some of that away. Notice they specify some of the B. If you took away all of it, you wouldn't have a reaction anymore. But in this case, it turns out
there is actually no stress, according to Le Chatelier, because solids are not included in the equilibrium constant expression K. And since solids aren't included, they will have no effect on the location of equilibrium for this reaction mixture. So watch out. That can totally be a thing where your answer is, haha, just kidding, the system didn't shift at all. That is still a legit Le Chatelier question. States of matter matter. Now, I'm sure you're excited to know. Now we're going to actually try this by answering our own free response questions. It's going to be very exciting. Okay, so I don't always expect you to list out these 1, 2, 3, 4, these steps and answer the question specifically before you start writing, but it is a good place to start. You have to make sure that you can conceptually answer the question before you can eloquently explain your understanding. So I would like you to take a moment, looking at this question, all of your knowledge of Le Chatelier, and I would like you to identify the stress, its effect, what is it counteracting, and how that answers the question. Just very briefly, and when you're ready to check your answer, go ahead and unpause the video. Okay, so in this problem, the stress is that we are decreasing the volume of the container. Now, if you recall, changes in volume basically cause changes in pressure, and that only affects gaseous systems. And we're looking at a gaseous system. But it all depends on the number of gas particles on the reactant versus the product side. Crazy story, for this particular system, you have equal number of gases on both sides, which means decreasing the volume actually has no effect. And now you just need to, write it out in words. It would be a great idea for you to try that. I know you think this is a silly practice problem because nothing happened, but explaining why nothing happened is really important. So when you're ready to check your answer, go ahead and unpause the video. Okay. Check your answer. How did you do? Did you hit the important points? Notice I was very specific about saying the reaction has an equal number of moles of gaseous reactants and gaseous products. I didn't just say like, oh, well, the gas numbers are equal, or the moles of gas are equal. The moles of gas where? You have to be specific. That is the key word for all AP Chemistry free response. All right, on to the next. Okay. As you know, we are going to start this off by making sure you can answer those 4 fundamental steps, and then we're going to combine that into a glorious free response answer. But first, you need to make sure you can answer the question. So please pause the video, try these, and when you're ready to check your answers, unpause the video. Okay, this particular problem, we have an endothermic reaction, and we are increasing the temperature. It is essential in your answer to specify that you know it's an endothermic reaction, because it's the only way we can figure out what happens. Well, because it is endothermic, increasing the temperature is like increasing a reactant, and so the effect, it will cause it to shift right, away from heat. And how does this counteract this stress? Well, you're using up some of the heat you added. What's sneaky about this question is they're asking you the effect on the calcium carbonate, a solid reactant. So a lot of us instinctively would go, oh, it's a solid, not going to do anything. Well, it's not going to change the concentration. Its concentration is constant. But if you are shifting right, which means you are making more products, you absolutely are using up reactants. So it is going to decrease the amount of the solid calcium carbonate, even though the concentration remains unchanged. Now, an important point. You, in answering the question, do not need to say that it decreases the amount, but it won't change the concentration because the concentration is constant. I'm saying that to make sure you know that so you don't include it in your answer. But that part does not have to be included, and in fact should not be included on your free response answer. Okay. It is time to take all of that beautiful information and combine it into lovely words and coherent sentences. So take a moment, attempt this on your own. When you are ready to check the answer, unpause the video. And there you have it. My version says, increasing the temperature of an endothermic reaction will cause the system to shift right to use up some added heat. This will use up some of the calcium carbonate, a reactant, which will decrease the amount of calcium carbonate present. Done. All right, there is one more practice problem on this page, but guess what? This is all you. You are going to try this. You know you are. You're going to try it, and then you're going to check your answer on the answer key to see how you did. Okay, after you have tried that and checked the answer key, go ahead and come back to the video because we have one last thing to talk about. Equilibrium as represented graphically. All right, if you're back at the video, that means you absolutely have tried the Le Chatelier free response practice and the world is making sense, or starting to. So now, let's try something entirely different. First, quick review. There are two different graphs that are commonly used to represent the basically systems approaching and reaching equilibrium. The first graph is when you're looking at the graph of the rate of reactions, like the forward reaction, reverse reaction, and you're looking at that over time versus time. And the idea, of course, is when the forward and the reverse reaction rates are both equal, you have achieved equilibrium. Now, in the second most common graph type, you're looking at specifically reactants and products, not rates. So this is an amount or concentration. And so the idea here is that they are most likely, the concentration of reactants and products are most likely going to reach equilibrium and not be equal, but they should be constant. So once the concentrations are constant, as time passes, you have achieved equilibrium. Okay, that's well and good, but you might be thinking, what does that have to do with Le Chatelier? Well, Le Chatelier, if you graph a system, you can actually see in the graph where a stress is applied and then how the system shifts to reestablish equilibrium. And by looking at the graph, you can actually predict what change or stress was applied. It's pretty awesome. Let's take a look. The first applied stress is probably the most common one, changing the concentration of something. Now, when you are looking at these graphs, it is essential to make sure you know which ones are the reactants and the products. So carbon monoxide and chlorine gas, totally not toxic at all, are your reactants. And then your product is this strange conglomeration of them. Well, notice we are looking at specific reactants and products. So we're looking at concentration versus time. And at one point, we have already achieved equilibrium because there was a point in time when the concentrations of all of these became constant. And then we messed with it. Something happened. And you have to figure out what. Well, the dramatic spike upward here shows you that the concentration of your carbon monoxide drastically changed instantaneously. Well, the only way that would happen is if you're adding more carbon monoxide. So that dramatic spike upward, that's the first change that was made. And you'll notice, well, we messed with the system, not at equilibrium anymore, so the concentrations won't remain constant. Le Chatelier says, and it's shown, that the reaction system is going to shift to use up some carbon monoxide to reestablish equilibrium. But did you notice, crazy story, when you reestablish equilibrium, you have never made it back to where you were before. We have counteracted some of the change, but not all of it. Now, the only way for that to happen, of course, is for the other two to shift as well. But notice they will have a more gradual or slower change. And those things are happening until all the concentrations become constant again. Okay, well, that's one graph. There's another graph. There's the rate versus time graph. So this one, notice it's looking at the rate of the forward reaction versus the reverse reaction. In this graph, you're starting with all reactants, no products. So your forward reaction at the moment you start is the highest it's ever going to be. But as the reactants get used up, the forward rate slows. As you produce products, now the reverse reaction rate starts speeding up, and eventually, hey look, they have reached equality between forward and reverse reaction rates, and thus equilibrium. Now you'll notice there's this crazy spike upward all of a sudden in the forward rate of reaction. And so basically what's happening here is that the rate's going to shift up in whatever, going to shift up. The rate is going to increase in the direction of shift. Since the forward reaction spiked, that means this reaction must be shifting right to reestablish equilibrium. And when equilibrium is reestablished, notice it is at a new position, a higher equal rate, because now there's more stuff. So you can graphically analyze almost any Le Chatelier shift using a graph. It is a little bit different if the applied stress is going to be a change in temperature. So if we're looking at the same system, you'll notice when you're changing the temperature and you're looking at those concentration versus time graphs, well, we started at equilibrium here. And then we're showing all of a sudden everything starts to change. But there's no spike. There's not so much the drama. And so in this case, what you're noticing is there's going to be a slow change in the concentration of all the reactants and products. And you can use your knowledge of where, like if you look at where equilibrium was reestablished, there was more of your product, right? Product went up, but your reactants went down. Well, that tells you the direction of shift. And so you either can figure out if it's endo or exothermic if you know the temperature change, or if you know if it's exo or endothermic, you can figure out the temperature change. There's many variations of questions, but the interpretation is going to show you, like, whenever the change in temperature, this one doesn't have that spike change. It has a slower change in all of them. Of course, it does actually have a spike change in the rate graph. So there's that. But for this one, what's interesting about it is it's harder to predict because you're basically going to spike up or down in the direction of the immediate shift. Here's where you can determine that this temperature change, it must have gotten colder because all of a sudden, rate drops. One of the reasons that these graphs can be complicated is you don't actually know if the forward or the reverse reaction is going to spike up or spike down. Well, it'll spike up if the temperature increases, but which one, forward or reverse? You don't know until you know if it's endo or exothermic. Similarly, it'll spike down if the temperature decreases, but which one? Well, gotta check if it's endo or exothermic. And then, of course, if one rate slows, the other one's gotta slow down too, but it'll slow down more slowly, like it did in this case, until they're both equal again. If one of the rates speeds up, then the other one's gonna speed up too, just more gradually. I love these graphs because they are a visual reminder of something very important. Nothing that you do can ever completely undo the stress on the system. All of these things were at equilibrium, they got stressed, and they found a new equilibrium, but it's not quite the same place. So the shifts predicted by Le Chatelier's principle will only partially counteract the stress. Okay, let's look at one more thing that we can show graphically. So in this case, our applied stress would be the addition of a catalyst. But hopefully you remember, when you add a catalyst, you're not changing the thermodynamics. You're not changing the location of equilibrium. You're just changing how quickly it gets there. So if you add a catalyst, your system will reach equilibrium at the same concentrations, but it'll happen at an earlier time. Of course, if you're looking at the graph of rate versus time, a catalyst will increase the rate of the forward and backward reactions equally. All right, magical chemists, that was it. So thank you for playing with the glories of chemistry.